discussion is all about the 5 types of chemical reactions. As we go through, we're going to talk about the type. We'll do a demonstration to show the type, and then we'll actually look at how to identify them if you're given a chemical equation. So the first thing that we want to do is just remember the diatomic molecules. This is in part A. We went over this in the D now, but you do need to make sure that you know all 7 of these diatomic molecules. So whether you remember H and 7, or you remember Bron H Cliff, you need to know that whenever one of these elements exists by itself, not in a compound, but by itself, you have to have that 2 as a subscript. So oxygen gas is O2. Hydrogen gas is H2. But when it's in a compound, right, it doesn't have to be diatomic. It's only when it's by itself. So the first thing that we're going to look at are decomposition reactions. So this starts at the top, right? Part B says discussion, 5 types of reactions. I gave you some space to go through and actually kind of give the definition, and then we'll go through and talk about each type as well. So a decomposition reaction, think about what decomposition means, right? Something decomposes, it breaks down. So in a decomposition reaction, we have a single compound, and I kind of gave this particle diagram example as well. If you want to draw the particle diagram as well, you can. These slides will go into Google Classroom, so you can go back and look at these as needed. So a decomposition reaction is when you have a single compound that breaks down. So this arrow means yields, right? You can think about it meaning produces. It separates the reactants from the products. So a single compound breaks down into 2 or more products. Typically breaks up into elements. So typically breaks up into its elements. So an example here shows KBr. So if you're like, well, how do I know that it's a decomposition reaction? All right, what would tell me that it's a decomposition reaction? Well, you have a single substance as a reactant. Right? Reactants are to the left of the arrow, products are to the right of the arrow. You have a single substance as a reactant. The only thing that can happen to that single substance is that it breaks down. So it's going to break down into the 2 elements that make it up. So one of them is K, one of them is Br. Now you'll notice with this particle diagram, one of them has 2 atoms, one of them has just 1. This is K. Bromine is one of those diatomic molecules. So whenever bromine is by itself, it has to be Br2. Right, this is not one of the examples that's in here. This is just something additional. Everyone is going to have some sort of picture like this just so you can see it. If you want to add the picture kind of down in here, you can. If you're like, I'm good without the picture, that's okay. Like I said, you can come back and refer to these whenever you need to. But with this, again, a single compound, a single substance breaks down into its elements. That is a decomposition reaction. So we have this single compound breaking down into its elements. Right? So if you've heard of elephant toothpaste, that's what this is. All right, so, oh, it has sound. Okay. We don't need the sound. Okay. All right, so this just keeps, right, giving off more and more soap. It's just hydrogen peroxide. When it decomposes, it's decomposing into its elements. So if we look at this first example, this is hydrogen peroxide. Now, look at your notes page. Yours says H2O. Add this subscript 2 after. It should say H2O2. that second subscript got removed somehow. Right? H2O2 is what it should say. Now, this is a decomposition reaction. You have a single substance on the left-hand side. The only thing that it can do is break apart. So look and say, okay, well, what are the elements that make this up? The elements that make this up are hydrogen and oxygen. Now, this is where you need to know your 7 diatomic molecules. All right, so I'll say keep in mind diatomics. The 2 elements that make up hydrogen peroxide are hydrogen and oxygen. Hydrogen, when it's by itself, exists as a diatomic molecule. It exists as H2. Oxygen, when it's by itself, exists as a diatomic molecule. It exists as O2. Now, in this case, we want to balance it as well. 2 H's, 2 H's, 2 O's, 2 O's. This is already balanced. So the bubbles, right, the reason that the soap was coming out was because the soap was catching hydrogen and oxygen gas that was being produced. So the soap, right, without the soap, you don't actually see anything happening because the gas is just escaping. If we look at 2 other examples, so again, if you say, how do I know that this is decomposition? When you have a single substance, right, a single substance as a reactant, the only thing it can do is break apart. What are the elements that make up KClO3? What's one of them? We have potassium, K. So I'm just going to do K. What's another one? Chlorine, right, Cl. And then what's the third one? Right, oxygen, O. There are the elements that make up potassium chlorate. Now always check when you write products, always check to see, are any of them diatomic molecules? Are any of them part of Braun H. Cliff? Well, Cl is diatomic. It exists as Cl2. Oxygen is diatomic. It exists as O2. There are the elements that KClO3 will break apart into. Now, here's where we're practicing balancing equations. This is not balanced. This is where balancing comes in. Because you're not just going to say it's K and Cl and O3. No. Cl exists as Cl2, O exists as O2. Then you put coefficients in front to balance. So 1K, 1K, that's good. 1 Cl, 2 Cls. Right. That's not balanced. I need a 2 in front. Remember this 2, this coefficient goes to everything. So now my chlorines are balanced, but now I've put a 2 in front of potassium. Put a 2 in front of potassium. Now count your oxygens. Remember, you save oxygen for the end. 2 times 3 is 6. Over here, there's only 2. So put a 3 in front. So your coefficients are 2, 2, 1, 2. Your reactant decomposes into its elements. See if you can write the elements for the third example. Calcium carbonate, that's chalk. Right, calcium carbonate is chalk. Break that up into its elements. So write what your products would be. All right, talk to people around you. All right, pay attention to your diatomic molecules as well. So you break it up. All right, you break it up into its elements. The 3 elements that make this up are calcium, carbon, and oxygen. Oxygen is diatomic. Oxygen is diatomic, so it exists as O2. Then you can balance. All right, then you can go in and balance. 1 Ca, 1 Ca, 1 C, 1 C. 3 O's, and 2 O's. Oxygens are not balanced. Remember, when you have an odd number, 3 is an odd number. Put a 2 in front as the coefficient. That's going to make it even. So now if you look, this 2 goes to everything. Since I was working with oxygens, I'll just focus on that right now. 3 times 2 is 6. Now we have 6 oxygens. What can I put in front of this to equal 6? 3. Now check everything else. 2 calciums now. I need 2 calciums, 2 carbons, 2 carbons. So now that's balanced. So this is just practicing balancing as well as looking at the types of reactions. So again, a decomposition reaction takes a single substance and breaks it down into its elements. You tell it's decomposition when you have a single substance as a reactant. Okay, let's look at the next type. All right, so now we're going to look at synthesis or combination. I don't care which name you use, whether you want to use synthesis or you want to use combination, they mean the same thing. I typically say synthesis, right? You're forming something. Other people like saying combination because you're combining. So a synthesis reaction, notice the particle diagram here. You have 2 things combining to form a single substance. It's like the opposite of a decomposition reaction. So you have 2 or more substances, typically elements, so 2 or more substances, typically single elements like potassium and bromine, combine to form a single new substance. All right, so we form a single new substance. So here we have potassium and bromine combining to form a single new substance. Now there are things we have to take into account here. All right, so some things we have to take into account here. Whenever you form a new ionic compound, so now we're going to get back into crisscross and writing formulas. All right, everything is continuing to build as we get into chemical reactions. When you form a new ionic compound, don't forget to crisscross. So that's why I said your periodic table will be useful because that should have your charges at the top. So also take into account charges. Those are from your periodic table. Right, group 1 is +1, group 2 is +2. We skip the transition metals. Group 3, like aluminum, that's +3. Carbon is ±4. Nitrogen's family is -3. Oxygen's is -2. The halogens are -1. The noble gases are 0. So that's why here, notice how there's 1 potassium and 1 bromine. That's because we have K combining with Br. Take into account the charges. Potassium is +1, bromine is -1. When you crisscross, it's 1 and 1, it's just KBr. Now this isn't balanced, but we could go through and add coefficients to balance it, and we will do that in the examples, but you have to take into account the charges and crisscross. But here's another combination reaction. So you have aluminum and iodine. So aluminum is Al, iodine is I2, right? It's one of the diatomic molecules. And what you can actually do is you can add a few drops of hot water, and that causes a reaction to occur between aluminum and iodine. So you had just 2 solids initially. Notice how a gas is being given off. Well, there's one way to tell a chemical reaction has occurred. Right? You form fire, right? It'll spark and start to burn, so it's giving off heat. There's another way to tell that a chemical reaction has occurred. And then once it's done, right, notice it's a different color as well. So you're forming something new. Yeah, this also happened to my fume hood, and they were not happy. Sorry. So that's just showing another example. So if we look at this one, here's aluminum plus iodine. Now you're going to notice this is an S for solid, a G for gas. We can represent states of matter as well. Right now I'm not as concerned about states of matter. We'll focus on those later. I'm concerned about forming the products. So aluminum is Al, iodine is I. When iodine is by itself, it's I2 because it's diatomic. So when you have two single elements, the only thing that they can do is combine and form a single substance. When you write your products, right, and no matter what level of chemistry, this is always something, a very common mistake. Just write the elements themselves. Do not worry about what the subscripts were on the reactant side. You are combining aluminum with iodine. It does not matter that it was I2 on this side. You are combining aluminum with iodine. Make yourself a note to crisscross the charges. So, you're looking at your periodic table. Aluminum is here. Again, this is the AP periodic table. You have the green periodic table where we've labeled everything. Aluminum is +3. I'm going to put a +3 above aluminum. Iodine is a halogen, right? Next to the noble gases. Halogens are -1. Whenever you form a new ionic compound, ionic is a metal and a nonmetal, you have to look at the charges and crisscross the charges. So you crisscross the charges, your product that you get is AlI3. That's the new substance that was formed. And now you could go through and you could balance the equation. 1 aluminum, 2 iodines, 3 iodines. Right? You could go through and say, all right, odd number, I need to make it even, so I'm going to double it. Now I need 2 aluminums. 2 times 3 is 6. I need 6 iodines. A synthesis reaction is when you combine 2 elements to form something new. Let's look at this last one for today. So sodium and nitrogen. Right, Na, nitrogen is N2 because it's diatomic. When nitrogen is by itself, it's diatomic. You have an element and an element. The only thing they can do is combine. Sodium is going to combine with nitrogen. You look at your periodic table. Sodium is +1. Nitrogen is -3. When you crisscross, remember the point of crisscrossing is to tell how many of each atom we need to make it neutral. Right, 1 comes down, 3 comes down. Your product is Na3N. And you could go through and you could balance. Right, you need 3 NAs to make that balanced. Now you have 2 nitrogens here and only 1 here. But now putting a 2 in front means that this is no longer a 3, but instead it's a 6. And then this third example wasn't in the notes, but this is what happened when we combined magnesium and oxygen in the back. Okay, so these are the first 2 types. All right, these are the first 2 types of reactions.